Welcome all to this course, Calculus on Several Variables. In this first video, we will see what we are going to study in this course and how we are going to go about it. Recall that in calculus, we study functions from the set of real numbers to the set of real numbers, or sometimes from subset of the set of real numbers to some subset of the set of real numbers. And when we studied analysis, we noticed that many properties of class of functions depended on properties or the structure of the real line. Thus, in analysis, we spent a lot of time studying the structure of the real line and the concept of limits. Once we studied the concept of limits, the other concepts like continuity, differentiation, and integration were easy. Why? Because they were all limiting processes. And because we spent a lot of time understanding limits, these concepts became easier. This was the rough summary of what we learned in analysis. In this course, we will be studying functions from Rn to Rm. You might have already encountered Rn in your course on linear algebra. In Rn, you have tuples of the form x1, x2, x3, etc. up to xn, where each xi is a real number. Rn is a vector space, and you have seen linear maps from Rn to Rm. Thus, linear algebra is important for this course as a source of examples of functions from Rn to Rm. In addition, notice that the derivative of a function from R to R was a linear approximation of the function. And something similar will hold for functions from Rn to Rm as well. Thus, this will be another way in which linear algebra will play a key role in this course. Thus, brush up analysis and linear algebra so that this course goes smoothly for you. Now that we have understood the content of the course, let us discuss how we will go about it. As in analysis, we will start the course by studying the structure of Rn. However, the good news is that we have done most of the hard work already. In analysis, we already studied the structure of R, and in linear algebra, we studied the vector space structure of Rn. This alone is not enough, and we will have to define some additional structure which will enable us to define limits and continuity. However, this extra structure is not too complicated, and once we have this extra structure, the definition of limits and continuity is quite analogous to what we have seen for functions from R to R. This, however, is not the case when we come to differentiation. There is significant work required to generalize the concept of a derivative to functions from Rn to Rm. To do this, we will first consider two special cases. Case 1 is when n is equal to 1. That means we are looking at functions f from R to Rm. And case 2 is when m is equal to 1. That means we are looking at functions from Rn to R. We will first define derivative for these two special cases and use these two special cases to understand the more general notion of the derivative of a function from Rn to Rn. Case 1 is especially easy. Such functions are called curves. And differentiation of curves is quite analogous to what we have already seen. Case 2 is not so analogous. Therefore, once we have studied case 2, we will be in a position to understand the more general case of functions from Rn to Rn. But before we study the more general case, we will study integration. And when we study integration, we will be focusing only on functions f from Rn to R. Recall that an integral was something akin to a sum. Therefore, the function has to be real valued to talk about integration. Therefore, we will be studying only the integral of functions from Rn to R. Moreover, we will be focusing on functions f from R2 to R when we do integration. The more general case of functions from Rn to R is not so much harder to define. However, we will not study that for reasons we are going to see next. Once we study integration and differentiation, it is natural to ask if there is any analog of the fundamental theorem of calculus for functions of several variables. Recall that we saw two forms of the fundamental theorem of calculus. If there are two functions, capital F and small f, such that the derivative of capital F is equal to small f for all values of x, then integral a to b f is equal to capital F of b minus capital F of a. This was the first form. And the second form stated that if you have one function f from closed interval ab to R, you can define a new function capital F, which is defined as capital F of x is equal to integral a to x f. If we define capital F in this manner, then it can be shown that f dash of x is equal to small f of x for all values of x. Recall that it is this second form that allowed us to consider integration as antiderivative. And that is part of the reason why it is so important. In fact, in school we studied integration as antiderivative. But that was just a happy coincidence. I believe you would be able to appreciate the astonishing aspect of this coincidence even more when you see that we cannot really generalize this to functions of several variables. We can generalize the first form of the fundamental theorem of calculus. However, even that is not so easy. Various generalizations of these results are famous and you might have encountered them before. They are known in the names of Green's theorem, Stokes' theorem, Gauss's theorem, etc. The simplest of this is Green's theorem, which is the special case for functions f from R2 to R. Even the proof of this very special case is not so easy. In fact, it will be beyond the scope of this course to give a complete proof of Green's theorem. We will prove certain special cases of Green's theorem and we will discuss why it is difficult to prove the most general form of Green's theorem. And given that it's so difficult to prove even the most general form of Green's theorem, we will automatically understand how difficult analogues of fundamental theorem of calculus are in general. This, I believe, is one of the big differences between calculus and calculus of several variables.